give a talk at this very nice conference. I will talk about a joint work with Marco Falconi, Jonas Lampert, and David Morouskas, which can be found on the archive. And the outline of the talk is that I first want to introduce the renormalized Nelson model and the Schrödinger-Gordon equations. Afterwards, I would like to present our main results and give a sketch of the proof. So the Nelson model describes non-relativistic particles which interact with a quantized scalar field. And in this talk, I'm interested where one has n non-relativistic bosons. So the Hilbert space is the space of symmetric wave functions for n particles times the bosonic Fock space over L2. And elements in this Hilbert space evolve according to the Schrödinger equation, where the Hamiltonian Hn is formally given by this expression. So this looks pretty similar like the Fröhlich model we had in the talk this morning, but we look at n particles which couple to a quantum field, and the AK and AK star are the usual annihilation and creation operators, which are defined on the Fock space sector where one has small n field excitations by the following formulas. They satisfy the usual canonical commutation relations. And if we look at the Hamiltonian, we see that we have here the kinetic energy of the non-relativistic particles. And then we have the coupling to a quantum field where the form factor is 1 over square root of omega k. And the dispersion of the field excitations goes like square root of k squared plus 1. So we are looking at the massive Nelson model where we set the mass of the field bosons equal to 1. Then we have here the field energy, which is kind of the second quantization of omega k. I would like to consider this model in a scaling where one weakly couples to the radiation field, and the scaling is chosen such that if one has n field excitations, then with the scaling the kinetic and the potential energy are of the same order. And also for this model, this function 1 over square root of k is not in L2, so the Hamiltonian doesn't give rise to a self-adjoint operator. However, this model is even more singular because one can also not define this Hamiltonian as a quadratic form. But there is a renormalization procedure due to Nelson. Namely, one can consider this Hamiltonian with a cutoff parameter, and then one can subtract the lambda-dependent constant and then obtain a self-adjoint operator whose time evolution converges to the time evolution of the cutoff Hamiltonian if one subtracts the constant before. And this has been done by Nelson, and later there has been information obtained by the form domain of this renormalized Nelson Hamiltonian by Griesemer-Wünsch and by other techniques by Lampert and Schmidt. And what it's good to keep in mind for this talk is that the form domain of the renormalized Nelson Hamiltonian and the form domain of the non-interacting Hamiltonian only have the zero vector in common, because the non-interacting Hamiltonian is just the Laplacian and the field energy, and since this interaction of the form domain with H1R3 only has the zero vector in common, this follows. To get a glance of this construction of Nelson and also to introduce some notation, I would like to first define while operators, which, if one acts with them on the vacuum, create a coherent state, and then the cross transform. The cross transform is a while operator where this function now depends on the positions of the particles, and this then creates correlations between the particles and the quantum field. And we look, so to say, so Nelson also introduced here an infrared cutoff, but that's not so important. So I would say we are looking at this function without a lower cutoff. which decays like 1 over k to the 5/2. And if one now applies this cross transform to the Hamiltonian with cutoff, one sees that this interaction here of the quantum field gets replaced by these operators on the right-hand side. And in the original model, the decay of 1 over square root of k, omega k was a decay for large momenta of k like k to the minus 1/2. So we see here that we get a more complicated structure because we get, so to say, quadratic field operators. But this function here decays like k to the minus 3/2, which is less singular. Then the cross transform also leads to a direct interaction term between the non-relativistic particles, which involves a gradient which can be seen of kind of Pauli field style. And then there's also a constant which diverges logarithmically with the cutoff parameter. And what one can do now is one can look at the right-hand side, subtract the negative constant, and then one can make sense of the right-hand side as a quadratic form, which is bounded from below, which gives rise to a self-adjoint operator whose form domain is the same as the form domain of the non-interacting Hamiltonian. And then one can cross-transform back this operator with the cross-transform with cutoff parameter at infinity, and then one also obtains a representation of this renormalized Nelson Hamiltonian, and this is the representation I will use in this talk and which we also use in our work. Okay, so what I would like is I would like to look at the n particle limit, large particle number limit of the system, and look at the dynamics and approximate it by its mean field dynamics and the corresponding Bogoliubov dynamics. And the mean field dynamics, in the mean field dynamics, the field will be replaced by a classical field. So then one can think of for which states this will make sense, and kind of a central part is played in this context by coherent states, because coherent states basically behave like classical states. So if the system is in a coherent state, one can replace the quantum field by a classical field. So since we want to do this at every time step, then one can ask which kind of particle configurations lead to the creation of a coherent state. And one can motivate that this is the case if one looks at a Bose-Einstein condensate of particles, because then, so to say, the coupling to the particles in the field equation can be replaced by the mean field coupling, and one can then motivate this leads to a coherent state. So as a good guess, one could start with this product kind of state, which is also a state with little correlation, and then one can make this kind of propagation of chaos assumption that the structure also hold at later times. And if one does this, one can, for example, look at the Ehrenfest equations to see that the corresponding mean field equations should be the Schrödinger-Klein-Gordon equations. So the Schrödinger-Klein-Gordon equations describes then the evolution of the condensate wave function and a classical field. And the first equation is just a Schrödinger equation, where we now couple to a classical field. This is just a time-dependent constant. And if we look at the field, then we see that we can express the field in terms of a mode function. So basically, this is kind of the quantum field from before, but we just replaced A by alpha and A star by the complex conjugate of alpha. And this mode function of this field satisfies a second equation, where the first term, so to say, ensures that the freely evolving field satisfies the Klein-Gordon equation, and here we have a coupling to the density of the condensate wave function. So the condensate changes the field, and the field acts back on the condensate. So this is a nonlinear equation. And for later purposes, I will also define the energy of the Schrödinger-Klein-Gordon system, which is so to say, invariant under the evolution. And throughout this talk, we will use a result which, for example, follows from a result of Pecher, namely that the Schrödinger-Klein-Gordon equations are globally well posed in H3 plus H5 where this small H5 is a weighted L2 space, which is defined in the following way. So having said this, I can now present our first result. And to this end, I introduce a functional beta, where the first term already appeared in the talk of François Gauls. So here, basically, one looks onto the projector, onto the orthogonal complement of the condensate. In each particle component, so this counts the relative number of particles which are not in the condensate. And then we have a second part where we first subtract the coherent state, and then we count the excitations above the coherent state and put them in relation to the particle number of the non-relativistic particles. And our first result then says, so if we look at solutions of the Schrödinger-Klein-Gordon equations with initial data in H3 plus H5 and many body states which are in the form domain of the renormalized Nelson-Hamiltonian and which are normalized, then we get this kind of estimate. So if we consider initial states such that the right-hand side is small, we see that this functional is also small at later times in the limit n going to infinity. And this, so to say, then proves kind of the stability of the condensate and coherent structure during the time evolution. So this constant RT is the following one, so it depends on the H3 and H5 norm, and one can show that this grows like a polynomial in T. Also, like in the talk of François Gauls, one can connect these functionals to trace norm convergence of reduced density matrices. So if I look at the one particle reduced density matrix, by looking at the projector onto the many-body state and then tracing out the degrees of the Fock space and of all particles except of the first one. And if I also define the one particle reduced density of the field by its integral kernel, where the normalization is such that the trace is the mean particle number of the field divided by the particle number of the non-relativistic particles, then one obtains the following bound, so to say, where one can bound the trace norm, one can bound the reduced densities and trace norm by the functional beta. So for suitable initial states, we then see that the one particle reduced density matrix converges onto the projector of the condensate wave function, and such that the reduced density of the field can be approximated by this classical mode function. Okay, next I would like to discuss for which kind of initial states this is a good statement. And here I first want to remark that, so to say, for the product states, yeah?
Where's the renormalized
It doesn't enter here.
Oh.
Yeah. So I mean, here's the renormalized, the time evolution of the renormalized Nelson-Hamiltonian.
So there's a lambda there.
No. This is the Hamiltonian, which is defined in this way, that if you take the evolution with lambda to infinity and subtract the constant, then you get this time evolution. Or basically the time evolution of the Hamiltonian, which was defined here. But otherwise it's hidden in the result. But it appears exactly if one looks at the initial states because heuristically I wanted to start from this kind of product state, but this is in the form domain of the non-interacting Hamiltonian, and therefore it's not in the domain of the renormalized Fröhlich Hamiltonian. So the result does not hold for product states in a sense. But what one can do is one can use the cross transform and only, so to say, incorporate correlations for high momenta such that the state in terms of reduced density matrices still looks like a product state, but so to say is in the form domain of the renormalized Nelson Hamiltonian. And this can be done in the following way, so it's almost the same function as before, but now we take the cutoff from below and then we act with the inverse of the while operator of this on the product state, and then we put the correlations onto, so we incorporate it on momenta which are larger than capital K. So the momenta below are in this way kind of not renormalized, that's why the energy diverges logarithmically with K, but the good thing is that we look at the energy per particle, so we also get a factor of 1 over n. And in terms of this functional beta for the states, so to say, since we only incorporate correlations for high momenta, one can show that, so to say, this then also goes to 0 as 1 over k. And because of this factor of 1 over n, we can choose k to be particle number dependent, like epsilon nn. And for these states, we then get, so to say, that we obtain this result from theorem 1 with a rate of 1 over square root of n. Are there any questions? Yeah.
You said that the Schrödinger-Klein-Gordon system is globally well posed on H3, direct sum with H5 masses. Is that right? Is this L infinity time?
Sorry?
What about the time norm?
The time norm, so this is globally, so you're asking about the growth in time?
Is this L infinity in T? What is the solution space?
So the solution space is just a space without time. So to say the statement is that there is a H3, H5 half valued solution which satisfies the equations, and then one can show that kind of these norms, they grow polynomially, which on compact intervals would be L infinity, but so to say not global. Sorry. Okay, then I, so to say, want to look at the quantum fluctuations around the Schrödinger-Klein-Gordon equations. And to this end, it's good to factor out the condensate and the coherent state. And this can be done by a small modification of this excitation space from the 2015 paper of Levine, Nam, Servati, and Soloway. Namely, we can look at the many-body state and then subtract the coherent state. Then we can order, so to say, the remaining state in states where one has k particles which are not in the condensate and n minus k particles which are in the condensate. And this can be done by projecting, so to say, the first k particles onto the orthogonal complement of the condensate wave function and the other n minus k particles onto the condensate wave function. And then this vector can be mapped to the following space, where we here have a truncated Fock space which describes the k particle excitations with the tensor product of the bosonic Fock space over L2, which describes the excitations above the coherent state. And since later we will discuss different dynamics, it's good to keep in mind that this can be done for general U and alpha. And by this map, one then obtains, by the adjoint of this map, one then obtains a decomposition, so to say, of states in our Hilbert space in the following form. And next I would like to introduce the Bogoliubov approximation, and to this end I first look at the Nelson dynamics with cutoff. So I look at a psi lambda nt, which evolves according to the evolution of this cutoff Hamiltonian, and then I look at solutions of the Schrödinger-Klein-Gordon equations where there's also a cutoff parameter in the interaction, which I would say is not so important at the moment how they look at. But then I can look at the map with respect to these solutions, which maps psi and t onto the excitation space, and this chi lambda t then satisfies a Schrödinger equation, which is given, where the Hamiltonian is given by the following expression. And in the following I will always denote, so to say, this truncated Fock space one can also see as a subspace of a double Fock space, and all quantities with respect to the first Fock space, which, so to say, describe the particles, will be denoted by B. So Bx, Bx star are the creation and annihilation operators of particles excitations above the condensate. And also Nb will be the particle number operator, and Na will be the field boson number operator. And so to say, like Peter explained in this talk, the condensate wave function will show up after this mapping, but since we also factored out the coherent state, we also have a dependence of alpha t. And then, so to say, we have here operators which preserve the particle number, but then we also have operators which have two and more annihilation and creation operators. And with this operator, we now can also do Bogoliubov's approximation, which basically says that one can assume that the excitations above the condensate and coherent state are of order 1. And if this is the case, then we expect that this term is of order 1. And since we have a factor of 1 over square root of n, we believe that we can, so to say, neglect this one. And also, like in Peter's talk, here appears the square root of 1 minus the number operator of the particles divided by n. And one can, for example, also do a series expansion of the square root and then only wants to keep the first order. And if we do this, then one obtains the following Bogoliubov dynamics with cutoff. And now we would like to have a dynamics where we send the parameter lambda to infinity. And what one can do, what is no problem, is one can replace on this level the Schrödinger-Klein-Gordon equations with cutoff by the ones without cutoff, so by the ones we considered. However, one has to keep this cutoff parameter in this function k lambda here, because otherwise this Hamiltonian is not well defined. But by a renormalization procedure, which is kind of similar but a bit more involved to the one of Nelson, we can show the following statement. Namely, if we again look at a solution of the Schrödinger-Klein-Gordon equations with the same initial data, and we denote by u lambda t the unitary propagator, which is generated by this Hamiltonian with cutoff, then we can show that there exists a time-dependent and cutoff parameter-dependent constant, such that if we take the strong limit of the cutoff parameter time evolution and subtract the constant from before, then we get an evolution which is unitary, strongly continuous in T, and a Bogoliubov transformation. And yes?
Do you show also that you have a normal solvent convergence of this operator as is in the case for the Nelson Hamiltonian, or is just a unitary grouplet? Or perhaps does it follow from that you can conclude that you have a normal solvent convergence
we just consider the unitary group
but
directly.
I guess you can derive from it something close to it at least, stronger solvent convergence.
Then probably we can. I think, I mean, Nelson goes the other way around.
Yes, Nelson proves
he goes
this,
non-resolvent convergence and then this implies the convergence of the group, but we directly look at the group. So with this Bogoliubov dynamics, we can show the following statement. So again, we are looking at a solution of the Schrödinger-Klein-Gordon equations. And then we are looking at a chi, where we are on this double Fock space, and the perp U denotes just that it's the bosonic Fock space of L2 functions which are orthogonal to the condensate wave function. And if we look at chi's which are normalized in this space, we can show that there exists a quadratic form with dense domain such that the following estimate in norm holds. Where this psi n, so to say, is just this adjoint from the map, which gives you the psi n which you obtained from the chi before. So basically it says, if here this quadratic form doesn't grow with n sufficiently large, we get in the limit n to infinity a norm approximation of the many-body dynamics, where this alpha and ut evolve according to the Schrödinger-Klein-Gordon equations, and u of t is this Bogoliubov evolution I've defined before.
Sorry, I didn't understand. What is delta chi?
This is.
Thanks.
Yeah, so I phrased it in this way because this is a bit unpleasant, but there's an explicit description of delta chi, which is just this quadratic form where the NA are the NA and B are the number operators. This is the field energy, and this is the second quantization of the kinetic energy. But then, for reasons which I also explain later, there also enters, so to say, a unitary operator, this operator W, which can be seen as a dressing on the level of this double Fock space. And this operator W preserves the norm of moments of the number operator, but we don't know, but we also don't expect that it preserves the norm of the that it preserves, so to say, the domain of the kinetic energy, the form domain, because it's kind of the analog of the dressing. What we can then do is, since this is densely defined, we can use a density argument to show, so to say, for more general states that in the limit n going to infinity, we also obtain a norm approximation. So if there are no questions, then I would like to make a comparison with the literature. And about the mean field limit I described of the renormalized Nelson Hamiltonian, there exists a prior result by Siad Amari and Marco Falconi, where they, so to say, show by means of the Wigner measure approach a result which can be seen to be the analog of the reduced density result. They get a more general class of states, but without an explicit rate of convergence. And then, so to say, there are other non-relativistic quantum field models which have been considered and which I basically listed in the order of the difficulty, I would say, in this limit. And the one is the Nelson model with cutoff. And these results are about reduced density, so this is a bit off because it's about fermions. And in this result, we applied the technique Peter explained yesterday to obtain also a Bogoliubov approximation and higher order approximations for the Nelson model with cutoff. Then there are also two results for the convergence of reduced density matrices for the Pauli-Fierz Hamiltonian and the Fröhlich Hamiltonian. And then these results kind of reused that we can control the kinetic energy of the particles which are not in the condensate by means of the variance of the energy per particle. But for the Fröhlich model, this then means that the initial states must be in the operator domain of the Fröhlich Hamiltonian. And since so to say, since only the form domain coincides for the Fröhlich model with the free domain, we incorporate it in a similar way as I described before, correlations onto initial product states. This, however, would not be possible for the renormalized Nelson Hamiltonian because the cross transform cannot be used, so to say, to map product states into the operator domain of the renormalized Nelson Hamiltonian. But in a later result, I then rather use different energy estimates more in the spirit of the Levine-Schlein paper of 2015, where one only gets a condition on the expectation value of the energy. And then one does not have to implement the gross transform here, and also can prove a norm approximation. And so, in a sense, one can say, since the dressed Hamiltonian, the form domain of the dressed Hamiltonian is the one of the non-interacting one, the dressed Hamiltonian behaves a bit like the Fröhlich model, but its structure is way more complicated. And so this can be seen a bit as a starting point from where one could maybe think of to apply similar techniques. But I also want to point out that here the dressing was viewed as an evolution, and then also one obtained a mean field approximation of the dressing, and this we will also use later from this result, but we will also push it on the Bogoliubov level. So on a wider scope, one can say we look at the limit where the field, so to say, behaves classically, and this classical behavior of a radiation field can also be seen in different limits, like the strong coupling limit of the polaron, which appeared in the talk of Robert today, and in a partially classical limit where a finite number of particles weakly coupled to the radiation field. I think Michele Correggi will talk about this on Thursday. And one can also consider, for example, a classical limit where a particle with huge mass couples to the radiation field and then it behaves classically, or other limits where one in certain situations can approximate the quantum field by a two-particle potential. I would also like to sketch some similarities with mean field limits with two-body interaction, because we use many techniques which were developed over the years, and I could list much more, but I just list the one which are the closest. So we use the excitation map from the paper of Levine, Nam, Savati, and Soloway, which in the dynamical setting also was used in the paper of Levine, Nam, and Schlein, and we also follow their approach. And then we use also energy estimates in the spirit of this paper, but for the reduced density matrix, we have to combine them with energy estimates of the 2010 paper of Antti Knowles and Peter Pickel. And these energy estimates, to my understanding, also were priorly used in this works, and later also in this works, and probably in many more works. Yeah. So now I would like to give a sketch of the proof. And a central point is to keep in mind that this representation of the renormalized Nelson Hamiltonian, which I introduced on the second slide, can be used to write the time evolution in the following way. And what one can do, and this is the observation I said before from the article of Amari and Marco Falconi, is that one can think of the dressing, so one can insert a parameter into the dressing and can think of the dressing as an evolution by itself, which is generated by this operator, and this is just the B function with outcut of which appeared before. And then, so to say, this gives rise to the following dynamics, and one can think of this dynamics as kind of, this looks like a Nelson Hamiltonian without kinetic energy and without field energy, and with a complex valued but way more regular form factor. So then we will use that one can also look at the mean field equations of this evolution, and the flow of this mean field equations will later be denoted by d theta. And the mean field equations also look like the Schrödinger-Klein-Gordon equations without kinetic energy and without field energy. So before we had the Laplacian here, and then we coupled to the classical field, but now we have a different form factor in the field, and since we don't have the field energy, the non-interacting field doesn't evolve according to the Klein-Gordon equations, but is just constant, but we still couple, so to say, to U theta. So this was also considered in this work of Amari and Falconi. And in this work now, we also consider the Bogoliubov dynamics of this model. So we look at the excitation map with respect to this dynamics, and then many body state which evolves according to this dynamics. And then one can do a similar approximation like I showed before, but one obtains a Bogoliubov Hamiltonian which also looks similar, but which also doesn't have the kinetic energy here in the part for the particles, and also no field energy. So basically what we do is we write the evolution in this way, and then we do a mean field and Bogoliubov approximation of the dressing, and then we also do a mean field and Bogoliubov approximation of the dress dynamics. So in total there are kind of 9 evolutions, the 3 original ones, then 3 dressing evolutions and 3 dressed evolutions. And I hope you forgive me that I don't define the dressed evolution. The mean field evolution is basically the corresponding mean field evolution to this operator which appeared on the second slide. But I would like to avoid to define it and explain the strategy of the proof. Yeah, so here we have kind of this many-body evolution which can be seen as a dressing, evolving with the dressed evolution, and then undressing, and also the evolution of the Schrödinger Klein-Gordon equations. One can prove that it's the same like a dressing, evolving with the dressed evolution and undressing. And as a first step, one can derive a result for the dressed evolution. So this is this upper plane. And there we can derive a result which almost looks similar. So we start with this initial state, we evolve them, and then we see that in terms of this functional beta, we get an estimate with respect to beta with this initial states, but we also have a functional gamma. And this functional gamma, so to say, quantifies the kinetic energy of the particle excitations above the coherent state and the field energy of the excitations, above the condensate and the field energy of the excitations above the coherent state. And so to derive this result, one can use this energy estimates, I said, in the spirit of the paper of Levin, Nam, Schleim from 2015. And they're basically, so one can map these quantities onto the excitation space. Then this beta is the expectation value of the number operator, which one can bound by the expectation value of the generator of the fluctuation dynamics plus the number operator, whose time evolution is nicely behaved. And then one can do a Grönwall estimate and bound then this operator by the number operator plus the kinetic energy of the particles and the field, which gives rise to this functional gamma. So the next step, what we would like to do is kind of to undress these quantities on the left and the right-hand side. And since the evolution of the dressing is quite regular, this can be done for the functional beta just by a Grönwall estimate. But what is less easy, so to say, is to undress this functional gamma because we don't expect, so to say, that we can undress this functional gamma because this would say that the dressing leaves the domain of the kinetic energy invariant. And for this reason, then we use this energy estimate of Pickel and Knowles, which can basically be viewed in this way. So we can look at the energy per particle minus the mean field energy, and then we can just insert here the cross transform, which gives us here of this transformed state the expectation value of the cross transformed Hamiltonian. And then one can also write this energy of the Schrödinger-Klein-Gordon equations as an energy functional which is invariant under this evolution SD, which is kind of the mean field evolution of the dress dynamics. And then acted on the dressed state. And
Sorry, what is D? Sorry, I got lost in the notation.
sorry, D is the flow. D is, so to say, the flow of the dressing equations.
Okay.
So here, this, so to say, U theta alpha theta is defined as D theta acting on U alpha. Sorry, thank you for pointing this out. And the solution, the flow of the Schrödinger-Klein-Gordon equations, I denote by S, ST, and the evolution, the flow of the dressed evolution, I denote by SD, and then sometimes I use the shorthand notation that E is D of 1. And so basically, one can dress the state and look at the energy function of the dressed evolution, and this is this. And what is then done is, in this energy estimates of Knowles and Pickle, here appears the kinetic energy plus the field energy plus the interaction. And here one can then insert the identity as projectors of P and Q, but onto the stressed states. And here one can insert, so to say, a coherent state of the stressed states and the inverse. And then these terms with P cancel with the mean field part for the particles, and here one can commute through this while operator, and then parts also get cancelled by the mean field part. But then we see that if we can estimate all other contributions, this term remain. So in this sense, we can relate, so to say, this gamma with stressing by the energy difference, which then gives rise to this estimate here, because the remaining terms are estimated by default. Okay, so next I would like to give a glimpse how one obtains the norm approximation. And there we can also first look at the dress dynamics. So we can start with an initial state, and then, so to say, look at psi n by mapping it back on the Hilbert space and evolving it with the dressed evolution. And then one can prove that this dressed evolution can be approximated by the decomposition from before, but the U and the alpha now evolves according to this dressed mean field equations. And here we have the Bogoliubov approximation of the dressed mean field equations. And since, so to say, the interaction is kind of singular, one needs to bound this by the third moment of the number operators and then also the kinetic energy and the field energy. And at this point here, this operator W does not yet enter. Where maybe I should point, sorry, where maybe I forgot to say. Sorry, I maybe should have pointed out that from the stressing evolution, kind of the unitary operator for the time evolution is denoted by W theta. So this is kind of the Bogoliubov evolution of this stressing evolution. And this does not yet enter here in this norm estimate, but we will see in a second why it enters. And then one can also prove a norm estimate for the dressing dynamics, which only requires certain moment bounds on the number operator because it's more regular. So we can look at an initial state which evolves according to the stressing evolution, which is obtained by putting this parameter in the dressing, and then it can be approximated by this decomposition where U and alpha evolve according to the mean field equations of the dressing, and here this Bogoliubov dynamics of the dressing evolution. So, and if one has this, then one can start, so to say, with the evolution which is generated by the renormalized Nelson-Hamiltonian. One can use this decomposition here to rewrite this evolution. Then we can use the second theorem to approximate this dressing here. And here it's called VD of 1, because that's exactly where the... so we have this dressing evolution which coincides with the Gross transform if theta is equal to 1. And then we can approximate here the stressing evolution by the corresponding Bogoliubov evolution. Then we can use the first theorem to approximate the dressed evolution here. And here then the dressed Bogoliubov evolution enters. And the reason why in this theorem 3 the operator W appeared was because since we first do this approximation here where we get the Bogoliubov approximation of the dressing, we look at this initial states, and if we use this bound of this functional d del d, this then gives rise to the quadratic form delta. And then in the last step, so to say, we still have here the undressing, but there we can use, again, the second result, so to say, to do the Bogoliubov approximation of this undressing. And in general, one could also define this as effective dynamics and be happy, but we also wanted to see how it connects to the dynamics which one obtains with cutoff, so to say, if one sends the parameter lambda to infinity. And if one wants to find this out, this then also proves the existence of the Bogoliubov evolution I've showed before. And how one does it is the following way. So I introduce a partially dressed mean field dynamics, which is obtained by the Schrödinger-Klein-Gordon equations and the mean field equations for the dressing, but I don't not dress until 1, but just until a parameter theta between 0 and 1. And then I can also, so to say, look at the dressing, where I now had to introduce a cutoff lambda, but that's not so important, and then consider, so to say, the time evolution of the partially dressed evolution. And this gives rise to a partially dressed Bogoliubov Hamiltonian and the corresponding unitary time evolution. So if we have, if we have theta being 0, then this corresponds just to the cutoff evolution because we haven't dressed at all. And if we set theta to 1, then this corresponds, then this is the generator, so to say, of the stressed evolution. And these operators can only be defined in the limit lambda to infinity for theta equal 1. And what we then show is that for all t and theta, we have the following equality, which says that, so to say, the dynamics with cutoff, where we subtract a constant which depends on time, lambda, and theta, is given by these 3 evolutions on the right-hand side, which are kind of the partially dressed versions with cutoff from the last evolution of the previous slide. And so this is a bit tedious to prove because I want to keep in mind that all these evolutions also depend on the corresponding mean field evolution. But how one can show this is kind of in a differential form, differential way of the statement. So one can show that kind of the evolution this evolution is kind of unique. Then we can take the derivative with respect to t, and if the generators of both sides coincide, then this should give rise to the same evolutions. And what one then knows is that for theta equals 0, the generators are the same. And then one can explicitly compute the time derivative of the generators with respect to theta and see that the derivative with respect to theta of both sides is the same. And this then can one let conclude the statement. And so to say then theorem 2 is then obtained if one looks at this quantity for theta equal 1 and takes the strong limit with respect to lambda, and there one then uses, so to say, the properties from these evolutions on the right-hand side. For example, there's strong continuity in lambda. And also one can then prove that these are kind of Bogoliubov transformations. And from this one can also infer that this evolution U of U and alpha t is a Bogoliubov transformation. So in summary, we have considered the mean field and Bogoliubov approximation of the renormalized Nelson model in a many-particle mean field limit. What is maybe a bit different to the other models is that one needs to do a renormalization procedure to make sense of the many-body and the Bogoliubov model, even if this is just a simple renormalization procedure by means of a constant. And the renormalization does not appear in the mean field equations, but it appears on the level of the Bogoliubov approximation. That it does not appear on the level of the mean field equations is maybe not so surprising, because the renormalization basically is obtained by applying, by subtracting a constant, and the functional beta and the reduced density matrices don't see a phase, so this is maybe expected. Yeah. So that's all I wanted to talk about, and I thank you for your
Thanks a lot, Nikolai, for the very nice talk. Questions?
I do have a couple actually.
Go ahead.
Okay. So thank you for the talk, because you, well, you saved me some time on Thursday. I think I can skip a lot of introduction. Anyway, no, my question is about two things. So the first one is about the restriction on to the massive case. So can you handle the massless case, and if not, is this related to the propagation of a number estimate?
No, so we think we probably can do, but it already was quite involved. And then treating both at the same time, I mean, doesn't look handy, so we didn't try. Okay. But so we just set the mass equal to 1, but per se we don't see an obstruction. Okay. Why, of course, maybe one has to work a bit harder, because in the massive case, the number operator is dominated by the field energy, which is then no longer the case. But still, we would not see any big obstruction.
I'll show you
maybe, for example, in this way, sometimes it then happens, if one cannot control the number operator properly, one could maybe modify this functional beta by putting the field energy instead of the number operator. I guess so.
I can show you an estimate on Thursday.
Okay, that's very good.
Okay, so I think, yeah, that's doable. And another question is about the stationary version of the problem. So
yeah, I mean, we just didn't try.
But that's again, it's doable again.
It's really interesting, right? but it's probably doable. Yeah, but it's more that we just started with the dynamics.
Okay, thanks.
There was another question, yes?
Yeah, so suppose that you start off with the cutoff model and then you compute the mean field dynamics. I'm assuming that the mean field equations are going to depend on the cutoff parameter. Can you show that the solution to these equations converge in a certain norm to the solutions that you have in the renormalized model?
I guess that one can show it, because the cutoff appears in the radiation field, yes. And since one is in this state h5 ½ basically, for example, if let's say I want to control the L infinity norm, and I call the classical field with cutoff this one, and this is the one without cutoff, then this is basically given by the L1 norm in Fourier decomposition. where I have 1 over square root of omega k, and then I get here the difference, so to say, of the cutoff. And then I also have the complex conjugate, but maybe I forget about it by putting the absolute value. But for example, a difference in L infinity norm would look like this.
You would also have differences of the alphas, no?
Yes, that's true. Okay, then you're right. It's probably a bit more involved. The statement I more wanted to make is you can, for example, do some kind of Markov type estimate, because this is just a cutoff which is above lambda. So you can multiply and subtract such that in the end you get here k to the 5/2 alpha, and then here you get the cutoff above, and then you get this is a 1 over square root of k, and then you also get k to the minus 5/2 in L2, which is really fast decaying. So there you see that it nicely converges. Of course, I didn't do it. One probably has to do a Grünwald estimate to show the difference of the solutions. But at this space, in this, I mean, it's a pretty regular space. There I would probably expect it.
So you can possibly conclude that the limits of large lambda and large particle number somehow commute in the mean field point of view. Yes. Basically, yeah. I think that's kind of the conclusion.
I mean, in the mean field, I don't see the limit of large particle number. So
I'm saying it from the point of view of the solutions of the mean field dynamics. It's just what you said.
Yes. I have to think about which limit where, but
Thank you.
Other questions? Yes, Sasha.
Yes, I have a question concerning theorem 2, namely exactly this U of t operator. It's like, I think he calls it Bogoliubov transformation. And so we make an exponential of some term, or if I recognize it correctly, it has bosonic and fermionic operator. So is it like
they are all bosonic.
They're all bosonic. So this is like a quadratic bosonic.
Yes, it's a Bose-Einstein condensate of particles which weakly couple to a scalar field with bosonic field excitations.
Okay, so maybe you have to explain it also a bit more after the talk then. But this is really like a bosonic Bogoliubov transformation.
Yes. So this is a bosonic Bogoliubov transformation on this double Fock space. So basically one can identify this double Fock space with the Fock space over the direct sum of L2 with L2. And in the space of L2 plus L2, one can then do, so to say, a Bogoliubov transformation for creation and annihilation operators which incorporates B and A.
All right. Thanks.
Jackie?
The purpose of embedding the particle into a Fock space was to get the norm approximation, but if you just do theorem 1, you don't really need to do that, right?
No. I mean, if I don't have theorem 1, one can directly do this on the n particle space.
Yeah.
But I mean, the reason is kind of so if one, for example, wants to show the well-postedness of the Bogoliubov equations, since we use this approach of Levin-Nam-Schlein, one proves some commutator estimates for the Bogoliubov Hamiltonian, and this kind of propagation of the reduced density matrices can be seen as proving some similar statements for the generators of the evolution. And then we already had the bounds for the on the excitation space for the Bogoliubov Hamiltonian, so it's just easier than to do it twice, but this statement can be completely proven without using this excitation space.
And also, my other question is, so your Bogoliubov transform, actually, there is a corresponding PDE, and you actually study that, right? I didn't see it.
So we know basically, what we know is at the end that it's the strong limit of the 3 evolutions we had on the right-hand side on the last slide. But then we can show that it's a Bogoliubov transformation, but so to say, it's kind of indirectly defined. In this sense, and that's, the point is a bit, I mean, this dressing here is not as easy as dressing with the Gauss transform, because one does not have a direct representation how one should just commute with the operator. So basically we define it in this way, and then we conclude the properties from this evolution. You can maybe see this as the explicit evolution, the right-hand side.
All right, so I would postpone another question to the coffee break, and let's thank Nikolai again.